before I introduce Joshua, I just want to mention two things. First of all, thank you all for coming. And then second of all, I just want to let you know that we have a Morgan Hill Half-Day Summit this Saturday. We have 3 great speakers. We have Hillary Freeman, who's going to be talking about her 50-year journey with diabetes. And then we have Mary Wright, who's a CDE at Kaiser, and she's going to be talking about your pump data and what to do with that data. And we also have Dr. Kumar from Lucille Packard, and he's going to be talking about sick day management and ketones. There's also going to be a vendor fair over there if you want to check out pumps, meters, different kinds of insulins. And the other thing is I want to talk about the walks. It's JDRF walk season in October, and CarbDM has a booth at all our walks. There's a walk coming up October 12th in Monterey, and the big one is October 18th at Great America, and we have a CarbDM and Brave Buddy walk team if you'd like to join that. And the last one is October 26th in San Francisco. So you can stop by our booth, join, have your own team, join our team, you're more than welcome. Okay, now Joshua. A lot of you may know Joshua. He's a Brave Buddy celebrity, so a lot of you might think he does not need an introduction, but those of you who don't know him, Joshua grew up in Silicon Valley, and he was a software engineer his whole life. His daughter Samantha, who's 13 years old now, was diagnosed when she was 18 months, and Joshua has been blogging for many years about finding a cure for type 1 diabetes. So,
thank you. Thank you. All righty. Oh. Of course.
Is it on? Yep.
Yes. Okay. Thanks, Noor, for hitting the highlights of my life in 3 bullet items. I want to make it clear that I blog very specifically about treatments that are aimed at curing type 1 diabetes and that are in human trials right now. And part of the reason I want to focus on that is why I care so much about clinical trials, that is testing on people. The FDA has a whole approval process. It takes at least 10 years. It may take longer, right? We don't have a cure. We know it takes at least 10 years. Nobody's gone through the whole process. It could take longer. And so by looking at cures that are being tested in people right now, I am looking sort of 10 years into the future. Because if it starts being tested in humans now, if it's successful, it might be available 10 years in the future. Also, a lot of research never ends up in human trials at all. We cure type 1 diabetes in mice sometime between 10 and 13 times per year. I kept track of this one year. Depending on how you count them, there were between 10 and 13 mice cures in a year. That same year, there were 0 human cures. So by focusing on the things that are actually being tested in people, it allows me to focus a lot more energy on a smaller number of cures, so I can really potential cures, so I can really understand all of them and all the issues involved in each one. At any given time, I'm typically following between 20 and 30 different research areas that might, I hope, lead to a cure someday. Part of this talk is talking about how close we are to a cure on these various treatment paths. And in order to understand that, you need to understand how the FDA approves things. The FDA has a whole process for approval, starts at phase 1 trials, 2, and then 3, and then marketing approval. All 4 of these things together takes 10 years at least, and a given cure could fail at any one of those points. It's very unlikely that it would fail in marketing approval, of course, but a lot of cures that I track end up failing in phase 1 trials, or 2, occasionally even 3. 3 by law, you have to have 2 separate phase 3 trials. And each one of those has to be large, 300 people typically. So that represents a huge amount of work. Phase 2 trials are usually between 20 and 100 people. Phase 1 trials are often just 10 people. But each one of these takes a couple of years. And so when sometimes people will say, oh, this might be a cure, or this might be on the market in 5 years. This might be on the market in 2 years. I try to avoid saying that because I never know the future. I'm very bad at predicting the future. What I can say is this treatment is going through phase 3 trials right now. So that means it's closer to the end. Another treatment might be in phase 1 trials. That's a lot farther from being used. So that, by using these points as milestones, I don't have to worry about all the uncertainties. But it's important to realize that it can fail at any point in time. Research is not a road that you drive down. Research is uncertainty. Okay, I was trying to find a metaphor for the whole talk, and I'm not sure I found a good one, but the metaphor that I'm using is one of maps and of travel. So, actually, before I go into this map, let me just give you a 30-second introduction to what causes type 1 diabetes. Type 1 diabetes is caused when your body's own immune system mistakenly attacks a very specific cell in your pancreas. And that cell is called a beta cell, and it's important because it generates insulin. So your body's immune system mistakenly kills the body's own beta cells, and then the person becomes a type 1 diabetic. Now, the path that I'm talking, so there are two fundamental ways of curing type 1 diabetes. What might be called the northern route, which is essentially to reverse both problems. First, you stop that autoimmune attack. But when you do, that doesn't immediately result in a cure because your body still has no beta cells and it still needs those. So then, once you stop the autoimmune attack, you then go on and either regrow beta cells, or you don't have to regrow them because you're in your honeymoon. One thing I didn't say about coming down with type 1 diabetes is the body takes a little bit of time, several months, to actually kill off all the beta cells. And somewhere in the middle of that process, you're not generating enough insulin anymore, and you are actually diagnosed as type 1 diabetic. But before you're diagnosed, you've gone through several months of losing beta cells, and after you're diagnosed, you go through several months where the autoimmune attack is killing the last of your beta cells. That period is called the honeymoon. So, if we could somehow stop the autoimmune attack during the honeymoon phase, that would be a relatively quick way to a cure. If we could stop it a little bit before the honeymoon, that would be even better. You'd have even more beta cells. But that's sort of one path to a cure. But the honeymoon only lasts a couple of months. After that, you have no beta cells at all. If we succeed in stopping the autoimmune attack after that point, then you need to actually regrow the beta cells that you already had. So then the cure becomes sort of this two-city tour in order to get to a final cure. The other way to cure type 1 diabetes, on this map, the southern route, is to replace beta cells with something that the autoimmune system cannot attack, or to put beta cells in a protected place in the body where, again, the autoimmune system cannot attack it. So these cures tend to be one step. And so if you can create beta cells or something that acts like a beta cell that can't be attacked by autoimmunity, then you've got the cure sort of in one step. Now I'm going to stop here for a moment and ask you to please ask questions while I'm speaking. This is complex stuff, and so if you've got any questions about this, please put up your hands right now so I can answer the questions. Yeah?
I thought I'd read something years ago that they discovered that even for long time diabetics, they could regrow beta cells many years later if you could stop the autoimmune attack, but maybe it's too slow, or was that just not true?
Everything you said is true, or at least believed by some people. So research is all about the unknown. So So right now, people believe that even long-term type 1 diabetics have a few beta cells still in their system. And most people believe that you can regenerate beta cells even after you've had type 1 diabetes for many, many years. But nobody knows how quickly they will regrow. So that road that says regrowing beta cells, that path might be really easy. It may be that your body wants to regrow beta cells, that all you have to do is wait around for a few days or a few weeks or a few years to regrow them. Or it may be that it's relatively easy for your body, if you like inject a growth hormone, you can get the body to naturally regrow beta cells. Or it may be that your body just won't regrow beta cells and you need a transplant or you need something else to help with that. That is one of the big uncertainties. And the reason that's an uncertainty is because we haven't cured autoimmunity, we don't know what would happen to a person after their autoimmunity is lifted, after their own immune system isn't attacking their own cells. Did that answer the question okay?
Yes.
Okay. Any other questions? Okay. Now, this map makes it look like everything is easy and obvious, right? This is the map that speakers use to explain what's going on. But in fact, this map is full of unknowns. That bit about the beta cells not knowing if they grow or don't grow, that's one of the unknowns. But the true map looks kind of like this. These trails down here refer to possible sort of one-step cures, ways that we could cure diabetes by replacing beta cells. The paths at the top are the ones that are different ways of stopping autoimmunity. You'll notice that none of those paths obviously get to a cure because we don't know. The research is about finding out which of these paths is going to lead us to a cure at some point in the future. So, you know, the previous map makes it look like all you have to do is travel long enough and we'll end up with a cure, and that's not true. The true map is a lot more like this, and we don't know which of these trails is going to lead us to a cure. So if you hear someone complaining, saying, oh, this will never work, we don't know. So now, I'm sorry, were there any questions about this slide in particular? Okay.
Is it to scale?
Is it to scale? As with everything else, the scale is unknown, and it would certainly be measured in years, maybe decades. That's the bad possibility. It might take us a long time. Okay, this is the first specific cure I'm going to talk about. It's encapsulated beta cells. This is one of the cures on the southern route, where if we get encapsulated beta cells and they work the way people hope they're going to work, it's a cure straight up. The basic idea is you take a beta cell and you encapsulate it in a membrane. The membrane is clearly the high-tech part of this, because that membrane has to allow sugar and nutrients and oxygen into the beta cells, and that membrane has to prevent the immune system from attacking those beta cells, and the membrane has to allow the insulin and the waste products that are created by the beta cells back out into the body. So the highest tech part of an encapsulated beta cell is the encapsulation. There are several different companies that are working on different encapsulated beta cell type cures. And each one of them is using a different kind of beta cell, right? Because the beta cell that's in the middle of this device could be from pigs, right? It could be from humans who have died and who have donated their pancreases, or it could be grown from stem cells. And different of these groups are researching with different kinds of cells. When I talk about pig cells in particular, some people get very nervous. And my advice is don't get nervous about pig insulin or pig beta cells. For many, many decades, all type 1 diabetics in the United States injected either pig insulin or cow insulin every day, right? The insulins that are made not with pigs or cows are relatively recent. So we know that pig insulin works, and there's a lot of good testing that pig beta cells, when encapsulated, will work just fine in people. So the 4 companies that are working, well, 3 companies and 1 research group. LCT is a New Zealand company. They've been in phase 2 trials for a long time. They have pig beta cells encapsulated with their own encapsulation technology. They've been in phase 2 trials a long time. The results from their phase 1 trial were good but not great. And they're continuing to do research to try to get a better encapsulated beta cell. These guys, ViaCyte, just announced that they have started a phase 1 trial. They're using beta cells which were grown from stem cells. This company is in San Diego, and I know there's a lot of local excitement about them. Beta02, I believe, is a European company, and they've announced that they're going to start a phase 1 trial real soon now. And finally, there's a group in France that's been running a phase 1 trial on a fourth device for many years and hasn't yet reported any results. Yes?
So how does the FDA determine when a company can pass from phase 1 to phase 2?
So the FDA doesn't really decide that. The company decides that.
Oh, okay.
The FDA, in theory, well, it's very complex. The FDA cares about safety when it comes to phase 1 and phase 2 trials. But if you've used a treatment in a phase 1 trial and there were no bad effects, the FDA will almost always allow you to go to phase 2. I don't remember any time when a drug that was found safe in phase 1 was prevented from going into phase 2.
So the only difference between the two phases are just the size of the trials, is that right? Or does the company themselves determine what the parameters of each phase will be?
Yes, but it's the phrase is in consultation with the FDA.
Okay.
And the reason is because at the end of the day, the FDA has to approve it for use in the market. And the FDA has very strict rules about that. So if the FDA looks at your research and says, you know, you're going to need 300 people in your phase 3 study, the company's going to have 300 people. For some drugs, like heart drugs, the FDA will say, you know, you need 3,000 people for that study. Then you can bet the company's going to do 3,000 people because otherwise it's a waste of time from their point of view. In my experience, the number for phase 3 trials for type 1 diabetes has always been 300 people. And you remember, you need to have 2 phase 3 trials before it's approved. But companies have a lot of leeway in terms of phase 1 and phase 2 trials, and the numbers range a lot bigger.
Thank you.
Yeah.
Can you describe the difference between phase 1, phase 2, phase 3?
The main difference, so what are the difference between the different phases? That's a big subject, and I don't want to spend a lot of time on it, but the simplest difference is size. Phase 1 trials are usually about 10 people. Phase 2 is usually 20 to 80, maybe up to 120. Phase 3 is usually 300. All those numbers are for type 1 diabetes trials specifically.
These companies and researchers that are in these phase 1, 2, are they actually working with humans or are these animals?
And no, these are all humans. Everything, almost everything I'm going to talk about is on humans. If it's done on animals, it's called a preclinical trial. So if you see the term preclinical, that means animals. If you see the term clinical trial or phased trial, those are always human trials. Yeah?
Isn't it true that phase 1 is usually safety-based or?
Sort of. So the FDA requires it for safety. What I've noticed is that for type 1 diabetes, the researchers almost always measure both safety and effectiveness even in phase 1 trials, because they don't want to waste their money on a phase 2 trial if it's not effective. So while the FDA requires them to look at the health of the people who get the treatment, the researchers choose to look at the effectiveness also. Any more trials? Sounds like next time I give this talk, I should talk more about the trials up front and then answer all those questions. Okay, any more questions? All right. Artificial pancreas. Not everyone considers this to be a cure. So I cover it partly because I'm interested in it, but partly because some people consider it to be a cure. And even if what's currently called an artificial pancreas isn't a cure, a lot of people think that if we could take an artificial pancreas and implant it into the person, that would be a cure, even if sort of a classic artificial pancreas wouldn't be. But let me talk a little bit about what I mean by artificial pancreas. An artificial pancreas is an insulin pump using existing technology, a continuous glucose monitor, again using existing technology, and a computer that reads the data from the continuous glucose monitor and controls the pump. And that computer is likely to be something very much like an iPhone or an Android device. You'll notice that those three technologies already exist. And so artificial pancreas is the idea of putting them all together and doing what's called a closed loop where the person doesn't have to intervene at all. There are lots of people working on artificial pancreas technology right now. I've listed 4 of them here, and plus there's at least 3 different companies that are working on it that I know about. So there's a lot of work going on with artificial pancreas, and you'll notice that all of these guys, all of the public ones, the researchers at universities, they're all in phase 2 trials. So this is closer to being available than anything else that I'm going to talk about. Artificial pancreases tend to come in 2 types. The first one, Dr. Damiano's work at Boston University, bihormonal. They call it a bionic pancreas because that makes for good marketing. But the basic idea is that artificial pancreas doses insulin and glucagon. Insulin lowers your blood glucose, glucagon raises it. It's like having a car with an accelerator and a brake. You have very good control. The other guys are all working on artificial pancreases that are insulin only. So that's kind of like driving with only an accelerator. You know, it's a little bit harder to do, but you can do it. Now, one thing I want to stress is that, hang on a moment. Oh, I complain about whatever it is. Okay. One thing I want to point out is the results at the bottom. Because these guys are in phase 2 trials, they've published a lot of results. The results for the bihormonal artificial pancreas, that can keep people in the 140s all day, 24 hours a day, all the time when they're eating sort of everything, on average. The insulin-only artificial pancreases can keep people around in the 150s. Again, that's the average of all the people in the study. Those are both great numbers. Okay? Now, it is true that the bihormonal one is doing a little bit better, but the insulin-only one is doing pretty well itself. Let me, to give you an idea of the differences, remember, these are both research prototypes. If these ever reach market, they're going to look a lot cleaner and nicer. The upper right-hand side is the bihormonal artificial pancreas, and you can see they've got 1 pump for insulin, 1 pump for glucagon, and that box, I believe, is their continuous glucose monitor. And then down here, this is what it looks like with just insulin. You've got an insulin set and 1 pump, and then over here, I think that's the continuous glucose monitor. Let me come back here. So you've got Ed Damiano, Dr. Damiano at Boston University. Havorka in Cambridge has been doing phase 2 trials. University of Virginia has one. These were, I think, the earliest guys to use an iPhone. LogicMD is a sort of consortium of like 4 different groups of researchers in 4 different countries. That's, what I'm trying to get across here is that the groups involved here are large. And that means it's closer to being ready than if just 1 or 2 researchers were working on it. Are there any questions about this?
So a lot of these companies have been playing around this area for a long time. Do you think they might buy some of these people, or do you think they're doing their own stuff, or how aggressive are they being?
It's very hard to tell. Medical device companies in the United States have a lot of restrictions about what they can say and what they can talk about. And in fact, they are not allowed to publicize certain things. So for all of those reasons, I know a lot less about what the commercial companies are doing, okay? But I will say that Medtronic is already in the market with a device that does one function of an artificial pancreas. It doesn't do the whole thing, but it will shut itself off if there's too much insulin on board already. That's the first baby step towards having an artificial pancreas, and that product has been available in Europe for years and in the United States for several months. So it's very reasonable to think that they are working on a follow-on to that. I mean, companies tend to work on follow-ons for products they already have in the market. But it's very hard for me to know about commercial products, is the bottom line. Are there any other questions? Yeah?
Well, I think one thing to know about most of the artificial pancreases is that they're not full, many of them aren't full closed loop, they're what they call a hybrid closed loop, where a person still has to bolus for meals.
Right, so the path to getting to an artificial pancreas may have some stops on the way. And one of the things people have experimented with, as Tamar mentioned, are artificial pancreases where you give them hints. And the hint is usually, I'm about to eat something. The hint might also be, I'm about to exercise in some cases. And some of these are in that category, some of these are not, and I can't remember exactly which is which. I believe that for Ed Damiano's group, Dr. Damiano's group, they actually did both, and so you can see the difference. And what I was surprised by was that the difference was not that great. The people who sort of forewarned the artificial pancreas that they were going to eat something, they had better numbers. But the people who didn't forewarn it at all and it just sort of measured the spike after the meal and dosed for it, those people had pretty good numbers too. Okay, are there other questions about artificial pancreases? Yes.
So in the bihormonal one, I'd heard that one of the problems was that the glucagon doesn't really last for very long.
Yes, so again, research is always about the future. So right now, glucagon is unstable and you have to replace the glucagon in one of these things every day. And that's a hassle, okay? Now, that's the bad news. The good news is that there are at least 2 different companies that are working on a stabilized glucagon. And the guys who are developing the bihormonal AP are hoping that that stabilized glucagon is going to reach the market before they need it. So that's one quick and easy solution to that problem. And the second quick and easy solution to that problem is to use an artificial pancreas that only uses insulin. And then if the stabilized glucagon comes to the market in 5 years, then we'll have the bihormonal artificial pancreas in 5 years. But it is important to remember that part of the prototyping phase is that they're replacing that glucagon every day right now. And they don't believe that that's viable in a commercial artificial pancreas. Other questions? Okay. Okay. There is more than one way to make an artificial pancreas. Another way to make an artificial pancreas is what I call a chemical barrier device. So this artificial pancreas is implanted. So it's inside of you, and all it contains is a reservoir. And next to that reservoir is a membrane. And the membrane serves kind of like a valve. And the membrane has been carefully chemically created so that if there's a lot of sugar in the environment, the membrane becomes permeable. And the insulin naturally flows out of the reservoir. On the other hand, if there's not a lot of sugar in the environment, then the membrane is not permeable and the insulin stays put. Now this is a very elegant design. It uses no electricity, it doesn't need a computer. If you can make that membrane properly, you can control blood glucose. And you can do it for a long time because you don't have any electronics. Unfortunately, nobody is testing this in people right now. This is one of the few things I'm going to talk about that hasn't been tested in people. However, there is one team in the UK that's working on this, and I'm hopeful that sometime they will start clinical trials. They haven't announced any start date, so I suspect that they're years away from starting such a thing. But it's another approach to artificial pancreases. It's a material science-based approach rather than a mechanical and electronic device-based approach. Now, if you take that idea sort of one step further, you have what's called self-dosing insulin. And the most I'm sorry, are there any questions about the chemical barrier one before I move on? Okay. Self-dosing insulin. It's a similar idea. You take insulin and you sort of chemically bind it so that it just sits there. But the chemical binding is sensitive to the amount of sugar in the environment. So if there's more sugar in the environment, the binder dissolves and the insulin goes out into the system and works. Similarly, if you put it into a person and that person's blood glucose level is very low, the binding stays put and the insulin has no effect on them. There are two companies working on this. Merck is working on it, and this group in India is developing a sort of a competing product, although it's a research group, so I'm not sure I'd call it a product. Again, this may not turn into a cure. This might turn into really, really safe basal insulin. So instead of taking Lantus once a day, you would take this once a day, and that would mean that, for example, it would be very rare for you to go low, that sort of thing. But if this works really well, it could turn into a cure, because in theory you could inject this once a day, maybe even once a week. You wouldn't have to count carbs. You would inject basically the same amount every week. It would be something very close to a cure. Are there any questions about self-dosing insulin or smart insulin? Yes?
Well, with either of these, if it's based on the membrane breaking down when there's sugar, when you get a high level of sugar, wouldn't all of the insulin or most of the insulin come out and, number one, leave you with none, and number two, overdose you?
So in actual testing on mice, this problem did not occur. It's an obvious thing to worry about, and I think that that's the reason why they've been working on this for years, and there's only 2 people working on it, and I suspect that those kinds of problems were what took them so long to get it to a point where it's almost going to start phase 1 trials. Just so you know, Merck has announced that it's about to start phase 1 trials. They said it was going to start this year. And of course, what I wanted to do was ask, is that Merck's fiscal year? Is that 2014? Is that 12 months from when they made the announcement? But of course, I can't ask and nobody else asked. So it's soon, but I'm not quite sure how soon. Any other questions about smart insulin or self-dosing it? Okay. Protected beta cells. So right now, if you take a type 1 diabetic and you give them a whole bunch of beta cells, you transplant them or something, it's not really a cure because they still have the autoimmune problem, and the autoimmunity will simply kill the new beta cells that you've implanted. However, at least one company is working on placing new beta cells in a different part of the body and they believe that simply by moving them, in this case into the liver, the body's autoimmune system will not attack them. This is based on the idea that the autoimmune attack is focused on the pancreas in some way that we don't fully understand. So simply by taking beta cells and putting them in the liver, they are hoping that the autoimmune system will not attack it and will end up with an actual cure for type 1 diabetes. This is the second thing, and I think it's the last thing I'm going to talk about, that is not in human trials right now. These guys have announced that they're going to start clinical trials next year, and of course that's every bit as vague as this year, except it's 12 months farther along. But again, if it works, it's a great idea. As someone who follows the research, there's no need for me to guess about whether or not it works. I just wait. If they test it and it works, I'm happy. If they test it and it doesn't work, I'm sad, but there's no reason to predict the future about whether it's going to work or not. Any question about protected beta cells? Okay. And there are some other possible places to put beta cells. For reasons that are not exactly clear to me, your immune system does not attack things that are in your own eye. I don't know why that is, but it's true. And so people have experimented with putting beta cells in eyes and seeing if they could cure type 1 diabetes this way. It didn't work. But it does give me hope that maybe there are other parts of the body or other ways to prevent the autoimmune attack from hitting new beta cells. Any questions? Yes?
You may be coming to that, but are you going to be talking about DRI's BioHub?
Okay, so the question is about DRI's BioHub. I don't cover it here, partly because what they're testing right now is not a cure yet. They're sort of testing basic technology that they hope will turn into a cure. So DRI is a big research operation centered in Miami, and they are working on something called BioHub, which is an encapsulated beta cell type cure. But they are very much keeping their options open, and they are testing different encapsulation techniques. And they are testing different mechanical containers to hold it. And they are testing and planting it in different parts of the body. And they're testing all these different things sort of in parallel, and the idea is that they'll choose the best of each answer and combine it into an encapsulated beta cell cure. But right now, I think the only thing that they're testing in people is the mechanical device that's going to hold it. But I expect them to start more human trials in the near future, and eventually they're going to end up testing an entire encapsulated beta cell. But right now they're not doing it, so they're not in here. Okay, any other questions about DRI? Okay. So now we've stopped talking about sort of the southern route, the cure all at once, and now we're looking at the first leg of the northern route, which is stopping the autoimmune attack. So one relatively straightforward way that people have tried to stop the autoimmune attack is by retraining the immune system. This is what happens when people have allergies, right? If someone's allergic to peanuts, they give them a little bit of a peanut protein. And then next week they give them a little bit more, and hopefully over